59. 2. All right, only got a handful of people. We'll wait a couple minutes.
Professor, can I ask you a quick question on the project while waiting?
Sure.
So for number 4, or for part 4, I mean, we need to put the layers of the table that is given to us from the patent. And I checked the definition of embodiment. It says the act of feeling, but I'm going to assume, like, is the first layer going to be air, or the silicon dioxide?
Why are we talking about embodiment?
Because it says embodiment on the table.
Oh, embodiment, to take the idea and make it into some physical form, probably.
Yeah.
Okay, so look at the table. If you look at tables 4 through 5 on page 6, so let me pull up. All right, tables 4 through 5 on page 6. Embodiment 5. So the embodiment of an idea is turning an idea into something physical or into something real or tangible. So embodiment 1, embodiment 2, yeah. I think lawyers use a lot of archaic terminology. I mean, remember, these are the people who say things like they're going to get a writ of habeas corpus, which is a Latin phrase.
Yeah. But I know it says the first layer is silicon dioxide, but shouldn't it be air? Because, in real life, air is the real first layer.
Okay, so yeah, they mean the first layer of material deposits. So what they're calling the first layer would be like the first thing that you would put in that list in the software. In fact, this would be a good time for me to share my screen and show you what's in there. So yeah, all right. On my screen, when you look in here, you see left medium index. That would be air. Right, or 1.0. Right medium index. Right now I have 1.5. That would correspond to polycarbonate, whose index is, substrate is another word for the right medium. A substrate is the thing that underlies all the layers. It's like the bottommost layer, the thing beneath the layers. So we would say that these 4 layers would correspond to whatever things we're going to put in coding layers. We'd have 4 pairs of numbers. And in each pair of numbers, you would have a thickness and then an index. And then right medium index would be whatever the index of polycarbonate is. So your indices would be, say, these if you were doing table 4. Your right medium index would be 1.58. Your left medium index would be air. Now, they're saying optical thickness of 1/4 of lambda. So if we were designing this for 550 nanometers, the center of the visible spectrum, we just take 0.55 microns and divide by 4, or we do something else?
It would be the wavelength, or the wavelength of the from the vacuum. So 0.550 divided by 1.47, or the 2, or the refractive index.
Yeah, so it's the wavelength in that material, which is the wavelength in vacuum, divided by this, or this, or this, or whatever. And then multiplied by 0.25 if you're following that table, or 0.8 if you're following this one, and so forth. Any other questions on that? All right, well, let's start by reviewing some facts about thin films. Last time we talked about off-axis cases where the angle of incidence is not just head-on. And what did we do if it was hitting it at an angle? So the ray is coming in, it's making this angle. And we want to figure out, somebody's told us, or somebody's asked us to design a coating. They say that for a wavelength of, well, I've drawn this purple, so let's stick with purple. Let's say for 430 nanometers, somebody's working with that for whatever reason. They want this to be an anti-reflection coating, because they don't care about the middle of the visible spectrum. They're doing something with purple light for one reason or another. So they want anti-reflection for 430 nanometer light coming in at an angle of, let's say, 60 degrees is our theta 1. And they tell you that this coating has a refractive index of 1.4, and it's on top of I don't know, BK7, 1.53. So let's think about this. And 1 is 1, and 2 is 1.4, and 3 is 1.53. Do we get a half cycle reflection phase shift there? This interface?
Yes.
Okay. Then some of the wave goes into the medium. What happens to the wave? Forget about even reflections right now. The transmitted wave. What happens to its angle when it goes into the medium?
It bends closer towards the normal.
Yep.
I think. Yeah.
So there's going to be a theta 2 is less than 60 degrees. And then some of that is going to be reflected. Now, the stuff here, is there going to be a reflection phase shift at the second interface?
No, there's not.
Oh, when it's in a medium with index.
Oh wait, yes, there is.
Yeah, because it's bouncing off of, I mean, it's got a fairly high index compared to air. It's 1.4, but it's bouncing off of something with an even higher index, 1.53. Okay, so second reflection has a phase shift of a half a cycle from the reflection plus the round trip. 2D over lambda over n2. And what do we multiply here by here?
And I'm not sure.
What?
Is it? Oh,
Oh,
is it the cosine of the angle?
Yep, it's cosine of theta 2. And the way to think about this is that I could rewrite this as 1/2 plus 2n2 d 2n2 cosine theta 2 over lambda times d. And so we could think of this, or I'll write it actually as this. Two d all of this divided by 2 pi. So 2 pi n2 cosine theta 2 over lambda, that would be kx times 2d over 2 pi. Right? We always think of it as being the component of the k vector that is going into the surface. And it's kx because the x-axis is horizontal and the z-axis will be out of the page and the y-axis will be vertical. So it's the component of the k vector times the round trip distance divided by 2 pi. We divide by 2 pi because 2 pi radians is a full cycle. All right, so if we want to figure out how many cycles, we have to divide by 2 pi. Any questions on that concept? Well, let's see here. The difference should be equal to just kx times 2d over 2 pi equals 2n2d cosine theta 2 over lambda. And if we want an anti-reflection coating, what do we want that to be equal to?
The m plus 1/2.
Yep. And from the examples we've done, what's the most advantageous value of m for an anti-reflection coating? Don't overthink it.
0.
0. So just 1/2, which means that d should be, well, if we do the algebra, we multiply both sides by lambda, divide by 2n2 cosine theta 2, and we're going to get lambda over 4n2 cosine theta 2, or 0.43 microns over 4 times 1.4 times is, let's see, is theta 2 60 degrees?
No.
Nope, because 60 degrees is the angle out here. That's the most common mistake I see when people solve problems involving this. So we know that sine 1.0 times sine of 60 degrees, that's n1 sine theta 1, equals 1.4 sine theta 2. Sine of 60 degrees is root 3 over 4. So sine theta 2 is root 3 over,
You mean root 3 over 2?
yeah, root 3 over 2. If I said 3 over 4, I'm sorry. Okay, so let's actually test this now with our program. So let's see here. I'm going to share my other screen. Now let's work out what that layer thickness should be. First, we need to have theta 2. Theta 2 is the arc sine of, what did I say? Square root of 3 divided by 2 times 1.4. Oh, okay. From NumPy, import, let's try NumPy dot arc sine. Let's try a sine. Square root of 3 divided by 2.8. From NumPy, import everything. Arc sine. Okay, now I forgot to import NumPy. That's, oh, you guys weren't seeing any of that. That's probably for the better. I was having some errors because I had forgotten to import some functions from NumPy. So theta 2 equals arc sine of square root of 3 divided by 2.8. And we get that for our answer. Now let's do cosine of theta 2. All right, we get 0.785. So then we say D is equal to 0.43, that's our wavelength, times 0.25 divided by cosine of theta 2. 0.1368. Okay, that's interesting that that's a repeating decimal. I did not expect that. So now in here, well, we've got BK7. So the refractive index of BK7 goes into right medium index. And our coating layer thicknesses, we're only going to have one layer here. And so that layer is going to have thickness 0.136818, etc., and index 1.4. Any questions on how I set any of that up? The software is all making perfect sense. You've had no problems thus far on the project? Good to know. All right, let's check what mode we're in. We're playing with the wavelength from 0.2 to, well, I'll take it down up to 0.3. No, I'll take it to 0.2. Yeah, we'll run with that. And we're working at an angle of, oh, we probably don't want an angle of 0 degrees. We want an angle of 60 degrees. And we get not at all what I expected. Ah, no. Not at all what I expected. All right, let's troubleshoot this. All right, let us troubleshoot this. We send it in at 60 degrees. Theta 2 is, well, let's see here. Sine of 60 degrees is √3/4. Zero 0.5 times the square root of 3 divided by 1.4. Theta 2. Let's check that by converting it to degrees to make sure it is smaller than 60 degrees. Times 180 divided by 3.14159. Yeah, that's smaller. So that makes sense. 0.25 times. Oh, you know what we forgot to do? Up here, look at what went into our calculation. We've got the 0.43, that's the wavelength in vacuum. We've got the 0.25, that's the 1/4. We've got the division by cosine theta. What do we leave out? Were we supposed to use the wavelength in vacuum?
Oh.
Index.
Yeah.
Oh, 097727. All right. Now let's try it. And the TE reflectance, the reflectance of one of the polarizations is clearly a minimum around there, although we could quibble over whether we got exactly. My controls aren't, oh Christ. Why is this? There is something weird. There's something weird that's been going on in Windows all day. When I'm in Zoom, it's not letting me do certain things. Let me turn off screen sharing for a moment and then turn it back on and see if that helps. No pun intended. I'm trying to zoom in on something in this graph and it's not letting me. But there's clearly a dip around 430-ish. When in doubt, you close the program and then you go back into the program. Breaking out of Zoom did not help, but when in doubt, you just close the program and go back in. Okay, I'm not going to maximize it because bad things happen when I maximize it. But let's first verify that we do have a dip around 430 nanometers or 0.43 microns. Yep, we definitely have that. Now let's look at the other polarization, which at least initially does not look like it has a dip around 430. It looks basically flat, maybe even peaked. And yes, it is. It is peaked there. We'll get into what's going on with the other polarization later. But for now, are there any questions about the polarization for which our results made sense?
Professor, I have a question. So for the solid line, there was a minimum, but we also see a maximum as well. Do we care about that at all?
Well, that's at much shorter wavelengths. In fact, that maximum is probably at half of 430 nanometers. And it looks like it is. Because remember, we looked at a much wider range of wavelengths this time. And if we had worked with either a shorter wavelength or a thicker film, the two are equivalent because it's the ratio of film thickness to wavelength that matters, then yeah, we could get, if we change the film thickness by a factor of 2, you might get constructive instead of destructive interference or vice versa. Does that make sense?
Mm-hmm. Yeah, but in terms of like just making an AR coding, that doesn't affect us, right?
Well, you can't really make an AR coding that's perfect at all wavelengths. Okay, you can only make an AR coding that has a dip at the wavelength you want, and hopefully the dip is wide enough that for a wide range of wavelengths you get reasonably low reflectance. That's really all that you can hope to do. Other questions? All right, then let's talk a little bit more about off-axis propagation and effects in thin films when we go off-axis, because it leads us into all sorts of important physics. All right, first of all, I was saying last time that we get a half-cycle phase shift when you reflect off of a higher index medium because of, well, we solved the wave equation and we looked at the reflection coefficient. But I did that for on-axis. What I want to do first is argue that all of that is still true if we look at off-axis. So let's say we have a wave that's coming in an angle θ1. And the incoming wave is e to the I times k dot k in dot r minus omega t. Well, let's see here. The components of k in, n1, n2, it'll be n k naught, that's the length of the vector, times cosine of θ1 x hat plus sine of θ1 y hat. So I can write this as e to the I n k naught cos θ1 x plus n k naught sine θ1 y minus omega t. Now a reflection coefficient, a reflected wave will have a reflection coefficient R12, and it's going to be going like this. So will the components of K reflected be exactly the same, or will at least one of them be different?
The X component will be the opposite.
Yep, because it's going in a different direction. It's not going in a completely opposite direction. The Y component is the same, but the X component will be different. So it'll be R12 e to the I times minus nk naught cosine theta 1 x plus nk naught sine theta 1 y minus omega t. And then the transmitted component will have a transmission coefficient again, e to the I times, let's see, now it's going at an angle theta 2. And I should have been writing N1 for all of these. All right. Any questions on how I wrote these down so far? Well, now let's think about what we need. We need to have that the wave is continuous. We need to have that E is continuous. And we need that the derivatives with respect to X and Y are continuous. Now, if we take derivatives with respect to Y, what are we going to, well, actually, first, let's just write down our conditions for continuity of E itself. If I plug in X equals 0, the field on the left side is the incoming plus the reflected. And what if I plug in X equals 0? I just get e to the minus I omega t, because, well, I get e to the I n1 k naught sine theta 1 y minus omega t plus r12 e to the I n1 sine theta 1 k naught y minus omega t equals t12 e to the I times n2 k naught sine theta 2 minus omega t. That's just plugging in X equals 0 and parts of the exponents go away. Now, is there anything that we can clearly cancel out right away on both sides?
E to the I, or e to the negative I omega t.
Yep, they all have an e to the minus I omega t, so we can just cancel that out. Now, if you look here, you're going to say, well, this one has nk naught sine theta 1 y, sine theta 1 y, and this one has n2 k naught sine theta 2. Oh, and I left out a y in there. Those look totally different. Are they totally different?
No, because of Snell's law.
Yep.
And one.
Yep, these are the same because of Snell. So in fact, all of this simplifies down to just 1 plus R12 equals T12. So this is exactly the same as one of the equations that we had last time. Now, we could also say, okay, well, we need continuity of the derivative with respect to y. If we take the derivative of one side with respect to y, we're going to get I n1 k naught sine theta 1. And on the other, and we're going to get that in both terms because n1 k naught sine theta 1 y is in the incoming field and it's in the reflected field. And the other one, we're going to get n2 k naught y sine theta 2. But again, by Snell's law, these two parts of the exponent are exactly the same. So they have the same y dependence. As far as the y dependence goes, everything is already continuous at x equals 0. It's only the derivatives with respect to x that will be tricky. And whenever we take a derivative with respect to x, for each term, we're just going to get plus or minus n cosine theta k naught I multiplied by e. And that's exactly like what we had last time when we didn't have any of these angles up in the exponent. We just had e to the I n1 k naught x and e to the minus I n1 k naught x and e to the I n2 k naught x. So everything's exactly the same except we replace n with n cosine theta. So I'm going to say n1 cosine theta 1 times 1 minus r12 equals n2 cosine theta 2 times t12. These are our two equations, and we just happen to have two unknowns, r12 and t12. Any questions? Well, the process is the same. We're going to isolate T12. We're going to isolate R12 by eliminating T12. So we divide both sides by N2 cosine theta 2. And I'm left with N1 cosine theta 1 over N2 cosine theta 2 times 1 minus R12 equals T12. But hey, T12 is also equal to all this up here. And then it's just a little bit of algebra. N1 cosine theta 1 over N2 cosine theta 2 minus all that mess times R12 equals 1 plus R12. Add this to both sides. Subtract a 1 from both sides. And now we can just divide both sides by this to get R12. And that is equal to N1 cosine theta 1 or N2 cosine theta 2 minus 1 over 1 plus N1 cos theta 1 over N2 cos theta 2. We're almost done. I'm just going to multiply top and bottom by N2 cosine theta 2 to simplify it a little bit. And we get R12 equals N1 cosine theta 1 minus N2 cosine theta 2 over N1 cosine theta 1 plus N2 cosine theta 2. Any questions? Well, we have to be a little bit careful here. Before, we didn't have any of those cosines in there. So we could just say, hey, if you're bouncing off a higher index medium, well, Our reflection coefficient is N1 minus N2. N2 is bigger, so there you go. Your numerator is negative. But now, okay, well, N2 is bigger than N1. Does that mean that N2 cosine theta 2 is bigger than N1 cosine theta 1? How would we figure that out? Probably the same way that we figured out what to do up here, canceling out n sine theta and the exponents. I'd look at Snell's law or Ibn Sal's law. What we have is, let's say that this is theta 1, is n1 and it's less than n2. Okay, if it's less than n2, does this ray get bent towards the axis or away from the axis?
Toward? Oh, wait. Sorry. Which one's larger?
If n2 is larger, does this ray get bent towards the axis when it enters medium 2 or away from the axis?
Towards the normal.
Okay. Let's see, theta 2 is smaller. So if theta 2 is smaller than theta 1, is cosine theta 2 larger than cosine theta 1 or smaller than cosine theta 1?
Isn't it larger?
Cosine theta 2 is indeed larger than cosine of theta 1. And n2 is larger than n1. So n2 cosine theta 2 is larger than n1 cosine theta 1. All right. So the same basic rules still apply when we want to figure out, was that first reflection giving us, or each reflection, when it's reflecting off of an interface, are we getting a phase shift due to reflection or not? And we just look and see, is it reflecting off of a higher index medium or lower? Any questions before we move on to a surprising consequence of this? Let's talk about total internal reflection. All right. And well, let's see here. So we've got medium 1 and 1, we've got medium 2 and 2. And our solutions to the wave equation are always going to be complex exponentials. All right, so now let's take the case that n1 is larger than n2. So we start off in the high index medium. If we're in the high index medium, n2 is the low index medium. So now the wave bends away when it goes into the second medium. So I could write it on this side as e to the I times k1x x plus k2 y y minus omega t. And on the other side, I could write it as e to the I times k2x times x plus k2y times y minus omega t. Now, these are the same on both sides. And if we're going to satisfy the wave equation, We'll just do it in 2D for now. N squared omega squared over C squared E. No, actually, I'll write it this way. I was skipping a step. N squared over C squared, partial squared E, partial T squared. Well, let's see here. That's going to be taking the derivative with respect to time. We get a minus I omega each time we take the derivative, minus I omega squared N squared over C squared. So that's just minus N squared omega squared over C squared E. All right, well, that means that kx squared plus ky squared equals n squared k naught squared. All right, or kx squared, kx is the square root of n squared k naught squared minus ky squared. So far, nothing profound. But what if it should turn out that k1y is larger than n2 k naught? So k2x, the x component of the k vector on the right side, is the square root of n2 squared k naught squared minus k2y squared. You might be thinking, well, okay, k1 is greater than n2 k naught. K1y is larger than that, but what about k2y? Well, the thing is, ky is the same on both sides, because ky is n sine theta k naught, which is the same on both sides. So k2x winds up being n2, the square root of n2 squared k naught squared minus something bigger than that. And if this something bigger is bigger than that, we get the square root of a negative number. Any questions? Somebody must have a question. If nothing else, question like, what on earth does this mean? K2x is negative. So, sorry, K2x is imaginary, okay? K2x is imaginary, so I'm going to write this as I times, it is conventional to call it kappa. That's just what every book uses, I kappa. Because the square root of a negative number is imaginary. So we get that K2x is the square root, or is I times the square root of n1 squared sine squared theta 1 k naught squared minus n2 squared k naught squared. Because I flipped this around, All right, I multiplied it by -1. And so we are left with this. We can factor out the K naught. K naught I square root of N1 squared sine squared theta 1 minus N2 squared. And if this, remember, we said N1 sine theta 1 is larger than N2. That's the whole definition of total internal reflection that we talked about at the very beginning of the semester. So the thing underneath the square root now is positive. We're taking the square root of a positive number. We get something positive. So we've got K naught times I times something positive. All right, well, that means that E2 is e to the I times I kappa x plus n sine theta k naught y minus omega t, or e to the minus kappa x e to the I times n k naught sine theta y minus omega t. Any questions on the procedure so far?
So we just rewrote K sub 2x.
What about k sub 2x?
We just rewrote it.
Well, we basically are just saying that k2x, that the x component of the k vector is an imaginary number. And when I take an imaginary number and plug it in here, I get I times I. And I times I is -1. So instead of getting something that oscillates, e to the I kx, I get something that decays exponentially, e to the minus kappa, or e to the minus, if you don't even want to think about where I got all these symbols around. I had an imaginary number multiplied by I multiplied by x. And an imaginary number multiplied by I becomes a negative number. So now I've got e to the minus something times x. So I've got something that decays.
Yeah, I was able to understand that part. I think I'm just I'm trying to see what substitution you made from when you went from I kappa to rewriting K sub 2x differently with the radical.
Well, K sub x, I said, is looking here, if I call these steps 1, 2, 3, 4, 5, or 6.
So for I think under the radical, I'm trying to, so I can see how you pulled out the I and that flips to the signs. I think the n1 squared sine squared theta 1.
Yeah.
So that whole first squared term, that replaced k sub y squared. Correct?
What about K sub y?
Sorry. So it's step 3. You have like a negative k sub y squared, right? Is
Yeah,
that what
so-
turned into the n sub 1 squared sine?
Sorry, your
Squared.
connection is also breaking up, so your voice has a lot of like,
Oh, I'm sorry. There's also like in the gardener and the mower is being really loud. Okay, I'm gonna try to type.
okay, so I see Ben's comment. I substituted KY as N sine theta 1 K naught. Does that help you? Okay. So we've got this exponentially decaying field. Now it's going to be, these numbers all up here, we're going to have like 1.5 squared. So kappa will be K naught square root of, let's say 1.5 squared minus, I don't know, often these numbers are like sine theta might be like 0.6, 0.8, 1.5 squared times 0.8 squared minus, let's say N2 is just 1, so we've got glass and air. All right, so we've got, well, let me just do this on a calculator. So like 1.44 square root of 1.44 minus 1, or K naught, these would be typical numbers, K naught times 0.66, or 2 pi over lambda times 2/3. So you'd get roughly, pi is about 3. Well, here, I'll just do it, 4 pi over 3. So you get about 4.2. These would be typical numbers, all right? So we would have that E2 is proportional to e to the minus 4.2 x over lambda. So that decays a whole lot within one wavelength. If we go just one wavelength away from the interface, E is decayed from whatever it was at the interface to e to the minus 4.2 times that. And by the way, this happens. People can actually measure this. All right, there are pretty straightforward, I mean, it's not trivial, but if you can measure submicron displacements, and there are ways of doing that, then you can actually see this. You don't necessarily have to have something with superb mechanical sensitivity. Honestly, just thinking off the top of my head, if I wanted to measure an effect like this, I would probably just set up a wedge, okay? And I would make it so that the spacing is 0 here and say 1 millimeter here. And this might be a few meters, let's say 2 meters. And if it was a really rigid wedge, then we could just say, well, okay, when is this some fraction of a wavelength? And, we'd have to go all the way down to about here for it to be some fraction of a wavelength, but we could do that. Or we could ask a question like, let's take a sphere and a sphere and a flat surface and press them together. And then we could see, okay, where is the gap where is the gap really small? And these are tiny predictable gaps. And then I would put detectors at different places along there and see what we get. But all of this is, in principle, measurable. People were able to measure this before they had, things that could do submicron precision alignment. Somebody must have a question. One thing you might be wondering is, what on earth is this good for? All right, so I've got a flat surface. All right, we've got air, or let's say water. We've got glass. Glass is the higher index medium, so we could totally have total internal reflection. Totally was not meant to be a pun. All right, we'll just kind of set it up like this. We'll send in a bunch of waves going more or less parallel to each other. And if I drew all the angles right, then they will be totally internally reflected. But there'll be a little tiny region where there's light. It's going to be, you know, a quarter of a wavelength or something. All right, 100 nanometers, give or take. But there will be a very tiny region in which some amount of light gets in. The field does not immediately go to zero. Now we were saying at the beginning of the semester, hey, look, no light gets out. Well, no light gets out on any of the scales that we, with our human eyes and human limitations, can see with our natural senses. Okay, the light is decaying on a much tinier scale than we can perceive. But right in this presence, just in this 100 nanometer or so region, there will be some light. And that light could excite fluorescence. Things that are just within that region could absorb. Now, sometimes, let's say that what we've got on the surface of this is a cell. We've got a cell sitting on this glass slide. Should be more like this. All right, we got a cell that's sitting on the glass slide. And a human cell could be about 10 microns in size. Human cells compared to, say, bacterial cells are pretty big. So that human cell is 10 microns in size. 100 nanometers, 1% of the thickness. But what if I only want to study 1% of the thickness? What if all I care about is what's happening at the membrane? Because a whole lot of important stuff happens at the membrane. The membrane is the interface between the cell and the rest of the world. And so what if I just want to study the cell membrane? Then maybe I want to put this cell, which is going to be in some sort of aqueous environment, on top of some glass and have the light in the glass come in at an angle that will give total internal reflection. And the light will only get like 100-ish nanometers in there. Actually, it's going to be less than that because the wavelength in water is smaller. So the light will get less than 100 nanometers in there. And the only things that will be able to absorb light and glow will be the things that are in that narrow region. And this is called turf microscopy, for total internal reflection fluorescence. Please, whatever you do, don't confuse it with other terms. There are other spellings. There's this one, which is completely non-controversial, but it means ground. And there's another one, which takes us to a whole bunch of social controversies on Twitter. I will just say that if you go on Twitter and use the word turf, unless you're talking to cell biologists, they're going to think something else entirely, and we don't want to go there. But please be very careful which version of this word you use. But total internal reflection fluorescence is the technique that they use, because it all just comes from recognizing that with total internal reflection, well, the components of the K vector depend on those angles. And if the angle in one medium is large enough, then in the other medium, we need one of the vector components to be an imaginary number. And what's an imaginary number? E to the I kx is e to the minus something times x. Any questions? Let's do one more thing with this and then take a break. One thing we could do with this is getting back to thin films. If I had reflectance off of just a plain surface, nothing, the light's going to go 100 nanometers and then decay away. But what if I have something like this? Theta 1. Then I have some evanescent decay, so it looks like this over here, and it hasn't quite decayed to 0. Then some light can get through, okay? So if this is comparable to the wavelength, or maybe half the wavelength, then some non-trivial fraction of the light can get through. And if a non-trivial fraction of the light gets through, then this is called frustrated total internal reflection, FTIR. Don't call it that in front of a chemist, because if you say FTIR to a chemist, they think that means Fourier transform infrared, and they will get very confused and think you're talking about something else. But frustrated total internal reflection, it's also called photon tunneling, because there are many mathematical analogies to tunneling in quantum mechanics. So we can go to our program and we could set this up. So I'm going to make my left medium something with a high index, let's say 1.8. I'm going to make my right medium glass. We're going to put a little air gap between, all right? We're going to have a little air gap. So we're going to have, let's start off with 100 nanometer air gap. And the index will just be 1.0. So something very high index, an air gap, and then glass. And we will work, let's see how this depends on angles. So fix the wavelength and vary the angle. So we'll go from minus 80 degrees to plus 80 degrees. And we'll just work with 500 angles, and we'll work in the center of the visible spectrum. Yeah, and we'll just see what happens. I better specify mode 4. Oh, great. All right, so if we look at the angle of incidence, we find that for one of the polarizations, for TE polarization, the reflectivity just goes up and up and up until we get out to 50-ish degrees. And that should actually make sense, because think about it, if you look at a piece of glass head on, like you can look right through the windshield of a car. That's the whole point of it, that you can look through it, you can see, you can drive. But if you look at it from the side, have you ever noticed if you look at the windshield from the side, it looks very reflective? Or if you look straight through a glass window in a house, you can see right through. You look at it from a side, it can be highly reflective. Drinking glasses are the same. There's a whole lot of things that are like that. They become more reflective as you look at them from an angle. And then eventually we get out to an angle where total internal reflectance happens. And then our reflectance is 100%. And don't worry about this other one yet. TM polarization is complicated. We'll either get to that at the end of today, or we'll get to it on Thursday. Any questions so far? Let's see if that angle where it happens makes sense. How do we figure out what angle we have to be at in order to get total internal reflection of the light that starts off in the medium with index 1.8? What's the equation we'd have to solve? Come on.
I'm sorry, I can't hear anything because of the lawnmower.
Okay, well, that's one person's excuse. What about the rest of you? Come on, somebody tell me, what equation do we have to solve if we want to figure out what angle we're going to get total internal reflection at?
Could we use Snell's law?
Okay, go on. So fine. So we're going to have N1 sine theta 1 and N2 sine theta 2. What's N1 in this case?
Do you want to define it as the incident angle?
N1 is an incident angle?
I mean, like in general.
The refractive index is an angle? Come on, man. Don't do that to me.
Okay,
What is
never
N1?
mind.
Don't do that to me.
Would it be
What?
in here?
It's 1.8. And N2 is what?
Is it 1.53?
1.53. That's the right medium index.
Oh. Oh, it's 1 for the coating layer?
Yes. So we're doing N1 is 1.8, N2 is 1, N3 is 1.53. And we would just need that N1 sine theta 1 is greater than or equal to 1. In general, greater than or equal to N2. That's the condition for total internal reflection. All right, because N2 sine theta 2 is always less than or equal to N2. I mean, it can't be larger unless sine theta was larger than 1. And sine theta can't be larger than 1 unless theta is an imaginary number. And if we're leaving out wave optics where we get these complex exponentials, well, then theta can't be an imaginary number. And so we just need to figure out this is the maximum value of N2 sine theta 2. So sine theta 1 should be 1 over 1.8. And if I go in and say, I'll share my other screen again, my mouse will work there. So I do arc sine of 1 over 1.8, and I get 0.589 radians. So I multiply by 180 over pi, and I get 33.7. That doesn't look right. Okay. Okay. So we're not getting total internal reflection at an angle of 33.7. But what if we're really getting the total internal reflection off of the glass? You've got this 1.8 medium, and then we've got light that somehow gets through the air, even though it's not supposed to. And then it doesn't undergo total internal reflection unless it gets turned around at the glass. So now let's solve that problem. $58.2. Hey, that looks right about, that looks more or less correct. Let's try that again. And this time I'm not going to maximize the window because something weird happens. Some other programs were doing this to me as well today. Okay. Now I'm not going to maximize it. Let's just zoom in and see roughly what angle that was at. Hey, that's at 58 point something. And we said over here, 58.21. Okay, this is minus 58, but whatever. And when I look in the upper right corner, that is pretty close to 58.2. That's 58.5. If I go over to here, that's 58.18. I just didn't sample enough points in between. If we sample more points in between, $58.24, $58.23 something. Anyway, any questions on this? So what you've seen here is that there is a way to defeat total internal reflection, all right, at least for a little while. You can defeat total internal reflection by having another material for the light to go into. Let's make that a little more explicit. Let's just make both media 1.53 and see what happens. Now we don't get total internal reflection. In fact, we only get, we don't get total internal reflection anywhere along here. Now let's see what would happen if we made the layer thicker. Now you see that we have to go out to much. Now we see that, yeah, we initially still don't get much reflection. We still get some tunneling of light across the barrier. We have to go out to larger angles to get that. Any questions? Sorry, I said that wrong. At those smaller angles, we get, never mind what I said. Let's take a break. I'll see you back in 10 minutes. All right. My teaching assistant has decided to join the class. I thought he was going to nap, but no, Bernardo, you know what? Let's put you on the floor. Yeah. Okay. All right. It is 6:28. So let's go back to a phenomenon that we have observed repeatedly, which is that one of those polarizations, the TM polarization, keeps behaving a little bit differently. In particular, there's often an angle where the TM polarization, the light that's reflected in TM polarization goes to zero. Let's review some facts about EM waves. So we've got an interface here, and we've got a K vector. K points in the direction that the field is going. And then we've got an E field, which is coming out of the page. And then we've also got a B field, which is perpendicular to the E field. And that B field, well, they're both perpendicular to each other. And if the light is called TE, transverse electric, what that means is that it is transverse or entirely in the plane. None of it, it's transverse to the interface. There's no component of the E field that's pointing into the direction of the interface. On the other hand, for the B field, there definitely is, because these things are really oscillating. And so by the time we get over here, all right. So my dog is raiding the garbage can. Of course, he does this when I lecture on Zoom. Good in the first half of class, then he gets some attention, decides to raid the garbage can. So it's transverse, meaning that the E field is transverse. It doesn't have a component that's pointing into the interface. But on the other hand, if we look at the B field over here, well, it's gone through a cycle of oscillation. It's gone through a half cycle. So it's at the bottom of its cycle. It's pointing like this. And I could take this vector here and I could say, hey, yeah, it has a component that's perpendicular to the, that's not going into the interface. It has a vertical component, and that vertical component is not going into the interface. On the other hand, that horizontal component is going into the interface. So this is not transverse magnetic. There is a B component going into the interface. On the other hand, we could come up with a transverse magnetic field. So I could consider another interface, another K vector, and I could just have the B field coming out of the page. So now there's no component of B that is going into the interface. There's no component of B that will push into the interface, but there is a component of E. Because E, well, it has a vertical component, but it also has an X component. And that X component is, in this particular situation, coming out of the interface rather than going in. Any questions so far?
For the first case, there is no E-field component, you said, going into the interface?
Correct. The first case is transverse electric, or TE. The second case is transverse magnetic, or TM. There's no B component into the interface. Now, I'm just going to make an assertion at this point, which is that the B field in this particular case satisfies a different equation. It satisfies the condition that, double check my notes to make sure I don't miss any of the signs. It satisfies this condition. Partial by partial x, 1 over n squared, partial b, partial x. Plus partial squared b, partial y squared equals where is something I don't like? I'm trying to do something on the fly, which is never a good idea. Equals omega squared over c squared. Yeah, I'm just going to take the equation that I actually wrote down instead of trying to translate it on the fly. All right. That is just what it is. Partial b by partial y is I ky b. And so we could say that minus ky squared b is equal to partial squared b by partial y squared. All of this comes from some boundary conditions that really go back to things done in 1520 and 2530. Because we're not going to get, if you want to take a more detailed wave optics class, we have our wave optics class with lab. I just want to understand thin films today. So I'm just going to take it as a given that one of these two types of waves obeys a different equation. And so if we try to solve for the reflection coefficients, doing everything that we did before, we still get one equation, which is continuity of the B field. And we're going to get 1 plus the reflection coefficient equals the transmission coefficient. But instead of trying to make the derivative continuous, we're going to make the derivative divided by n squared continuous. Okay? Because this is the thing that we have to take the derivative of with respect to x. And when we get to x equals 0, this is the thing that could be discontinuous if we aren't careful, if we don't impose a condition. So 1 over n squared times b is the thing that has to be continuous. Sorry, 1 over n squared times the derivative with respect to x So we're going to get 1 over n1 squared times I k naught n1 cosine theta 1 times 1 minus r1 2. Because remember, the incident field, the x component of the k vector is positive. It's pointing to the right. Then for the reflected field, kx is less than 0. That's going to be equal to 1 over n2 squared I k naught n2 cosine theta 2 t1 2. You cancel the I k naughts. And we have almost the same equation as before. Except we replace n cosine theta with cosine theta over n. And so if I just make that change, then R12 is equal to cosine theta 1 over n1 minus cosine theta 2 over n2 over cosine theta 1 over n1 plus cosine theta 2 over n2. All right. Now everything is more complicated. This is not necessarily negative if n1 is less than n2, because now we've got n1 in the denominator instead of the numerator. So a small n1 is a big 1 over n1, and a big n2 is a small 1 over n2. So everything gets a lot more complicated there. That's one reason why this doesn't always obey the same conditions. This polarization doesn't always obey the same conditions as the other polarization. It doesn't always obey the rules that we laid down so far. But there's another thing. Let's just figure out, when is this equal to 0? Well, let's see here. Let's just set cosine theta 1 over n1 equals cosine theta 2 over n2. And then we have to have some way of relating theta 1 to theta 2. Now, the only way I know of to relate theta 1 to theta 2 is Snell's law, which relates sines. But here we have cosines. So I'm going to use the fact that cosine theta is the square root of 1 minus sine squared theta. So then I can do 1 minus sine squared theta 1 over n1 squared equals 1 minus sine squared theta 2 over n2 squared. All right, well, what else do we know? We know that n1 sine theta 1 is equal to n2 sine theta 2. So sine theta 2 is n1 sine theta 1 over n2. I plug that in and I get 1 minus sine squared theta 1 over n1 squared equals 1 over n2 squared minus n1 squared sine squared theta 1 over n2 to the fourth, because we have an n2 squared in the denominator, and then we get another 1 over n2 in our expression for sine theta 2, and then we square that. Any questions so far? All right. 1 over n1 squared minus sine squared theta 1 over n1 squared. You know what? I'm just going to rewrite this as 1 over n1 squared minus 1 over n2 squared equals sine squared theta 1 times 1 over n1 squared plus n1 squared over n2 to the 4th. Now, if I try to go much farther than this, I run into the problem that we slog through basically an algebraic death march. And I don't really want to do that. So, okay. I see what we should do. At this point, I've got that sine squared theta 1 equals this bloody god-awful mess. Let's multiply both sides by n2 to the 4th and n1 squared. So I'm going to get n2 to the 4th minus n1 squared. Yeah, let's start over again. Multiply both sides by n2 to the 4th. I'm sorry, algebraic gymnastics. You know what? I'm not going to teach you anything through these algebraic gymnastics. What if I just assert that tan theta 1 is equal to the ratio of the refractive indices? How about I just do that? Because we've got 5 minutes of class time and 15 minutes of algebraic gymnastics. Well, if we do that, then let's switch back to what we were doing in the software. And let's go to a case we were doing before. We're doing angle resolved reflectance, reflectance versus angle. And let's make one of these 1 point. You know what? Let's make one of these 1.8. Let's just do this. Let's just do glass on the left, air on the right, and air in the layer. We can do that, okay? So the layer will have a thickness, but it's made of air, and then it touches air, so it won't really matter. And let's just plot that. And what we see is that for both of these, we eventually get total internal reflection. For both polarizations, we eventually get total internal reflection. But before we get total internal reflection, for the TM light, we get an angle with 0 reflection. That's called Brewster's angle. And Brewster's angle is really important. Now let's verify that these angles make sense. Let's do arctan of 1 over, arc sine of 1 over 1.53 That's the angle of total internal reflection. That should be at about 40.8 degrees. And sure enough, if we look at this, we get almost exactly at 40 degrees that we get total internal reflection. So let's do arctan of 1 over 1.53, which is where we said we should get 0 reflectance of the TM light. And we'll convert that to degrees. And that should be at 33 degrees, our formula predicts. And if we zoom in on here, sure enough, around 33 degrees, we get 0 reflectance. So what we have is a very interesting case where our reflected light will be 100% one polarization, okay? Our transmitted light will have both polarizations, but our reflected light will be 100% one polarization. Sorry, the dog is now eating some paperwork. What we're going to talk about on Thursday is what we can do with that and how we could make something more interesting out of that using a trick called a distributed reflector. So we'll do distributed reflectors, and we'll talk about how to do those with Brewster angles and also just use those for wavelength filters. And then we are going to start on diffraction gratings. So have a good night, and I'll be available tomorrow and Thursday morning if you have questions on the upcoming project.
I just had one quick question.
Sure.
So you said Brewster's angle is, which one is the minimum right there?
It's where you get 0 reflectance of one of the polarizations. So total internal reflection, you get 100% reflectance of either polarization. Brewster's angle, you get 0 reflectance of the TM polarization.
Okay, thank you.
You're welcome. You have a question, Leona?
No, sorry.
It's okay.
I got distracted towards the end.
No problem.
Bye. Have a good night.
You too.